Alrighty, so in this one, we're going to take a look at some more Year 12 like revision type stuff, looking at mechanics in the Tour de France. So let's start off with some fairly low difficulty question. So we've got Mark Cavendish. He's a sprinter in cycling, and he can generate a certain amount of power. If there's no air resistance, calculate the maximum velocity that he can essentially develop in a flat section road in 10 seconds. So if it's flat, there's going to be no GPE. So we can first of all work out how much energy change he can deliver. So that's going to be the power times by time. So it's going to be 1600 times 10, which is going to be 1.6 times 10 to the 4 joules. That's how much energy is available. So that's going to turn into kinetic energy. So half mv squared is going to be equal to that change in energy. So the velocity is going to be 2 delta E over m. So like this, and it's going to be the square root of 2 times 1.6 times 10 to the 4, ruled over 70 because that's the mass. And then when we put that in, we end up with a value of 21 meters per second, which is fairly speedy. That's the possible velocity. All right, so let's continue on. So Nibali is a different cycle rider, so he's not a sprinter, he's one of the general classification riders, and he's generally considered a good descender, so he can go downhill. So essentially he's going to be using the GP he has to his advantage. So you can see it's like coming down a mountain, so we've got a mountain, blah, blah, blah. So we know that this is 800 meters, and the end it tells you is 400 meters. So the change in GPE during this is going to be mg delta h, which is going to be equal to mg times 400. This is going to be transferred to kinetic energy, so half mv squared is going to be equal to mg times 400. So we can see the, not the g, the m. So the velocity is going to be the square root of 2 times 9.81 times by 400, which is going to give an overall velocity of 89 meters per second, two significant figures there. Okay, so fairly straightforward, just some basic energy transfers. Alright, so let's ramp up the difficulty a little bit. So we've got modern bike with suspension. So on a bike you'll typically have two springs that work in parallel each other. So the bike drops into a 10 centimeter rut, and you've got two springs of this total spring constant. So first of all, the equivalent spring constant is going to be 1.0 times 10 to the 4, so it's 5,000 times 2 newtons per meter. So what's going to happen is the GP is going to be transferred into elastic potential energy, which means that mg delta h is going to be equal to half kx squared. So we wanted to know how much it was compressed, so we want to rearrange to make x the subject. So we're going to have 2 mg delta h all over k, the equivalent one. So what we're going to have is 2 times the mass, which is 120, times 9.81 times 0.1, divided by 10,000, square root of that gives you a compression of 0.15 meters. There, that will be your total compression from the energy gained from losing GP. Alright, so we've got a force graph, which is a sine function, and a displacement graph, it looks like, with a cosine function. So we want to determine the phase difference between the two graphs. So a like for a general function, let's call it a general function. This in here with the multiplying, or whatever multiplies by your sine or cosine function, would be the amplitude of your wave. So that's actually going to have no effect on the phase whatsoever. So if we like sketch these graphs, the first one it says is a sine graph. So sine graph looks kind of like this. The next one is a minus cosine graph. So that's going to look like this. Okay, so the normal difference between a sine and a minus cosine graph would be pi over 2, but because inside these brackets we've got 2's, that essentially squashes the graphs. So what was in 360 is now in 180, or what was in pi 2 pi is now in pi. So what was a pi over 2 phase difference is going to become a pi over 4 phase difference between the graphs because of that scale factor multiplying t there. So that would be your phase difference. Alright, so the next one, we've got a cyclist traveling around a bend at constant speed. Use Newton's first and second laws to explain why the rider is accelerating. So if we sketch ourselves a bend, so at the start of the bend, the rider will be traveling at a velocity v, and we know it's constant speed, so when it reaches the end of the bend, going around here, it's still going at a velocity, or sorry, a speed, or we'll call it v. So what we've got done is we've gone from this, and we've ended up with this. So what must have happened is it's experienced a change in velocity that way and a change in velocity of that way, giving you an overall resultant change in velocity. So because velocity is a vector and direction is important, we must have experienced something to counteract this component, so a change in velocity that way, and another change in velocity that way, giving us a kind of, if you like, a resultant change in velocity. So acceleration is change in velocity over the time it takes. So if you get a value of a change, if you have a change in velocity term, we know it's accelerating. So in terms of explaining it using those two laws. Okay, so Newton's first law says the motion of an object doesn't change unless acted on by a resultant force. Motion would be like the velocity. So because the direction of your velocity or direction of your speed is changing, your velocity is changing, and therefore the motion of the object is changing, so you know it's been acted on by a resultant force. And what Newton's second law tells you is if it's acted on by a resultant force, it must be accelerating. So that's kind of the way of explaining using the laws, and then these diagrams help you see what's going on in terms of the vectors. So you've got in this next one, a 60 kilogram rider accelerating non-uniformly from rest 10 in 5 seconds. To calculate the average force provided by the rider. So if you think about Newton's second law in its general version, is this one. So that's going to be 60 final velocity minus the initial velocity in 5 seconds. So that's going to be 120, which is 1.2 times 10 to the 2 newtons, giving it to an appropriate number of significant figures for the data you were using. Okay, let's continue to the most challenging of this. All right, so let's have a look at the most challenging question, which I took from the Physics Olympiad, I think. So it tells you that initially in the question, the thrust force from the engine, so the force is equal to the weight force of the object. So that's going to be the mass times by g, so that's going to be 9.81 times 10 to the 4. So using Newton's second law, force is the rate of change of momentum. So let's rewrite that slightly like this, which means the rate of change of the mass of the object is going to be the force divided by the velocity. So that's this 9.81 times 10 to the power 4 divided by the velocity, which is 900, gives you 109 kilograms per second. All right, so that is your mass per second. So next it wants us to get the acceleration of the rocket when the fuel is almost exhausted. Okay, so we're essentially going to be using Newton's second law. So the resultant force acting on the object is going to be the thrust force of the rockets, but minus essentially the weight force of the object. So 0.2 times 9.81 times 10 to the 4, because remember it's going to have lost 80% of its mass, and then divide it by the total mass of the object now. So let's get rid of all these 10 to the 4, so it's going to be essentially 0.8 times 9.81 times 5, because divided by 0.2 is the same, which gives you 39 meters per second squared. There as the acceleration of the object. It wants the mass of the rocket at time t. So the mass at time t is going to be the initial mass minus 109 t. So that's going to be like essentially 10 to the 4 minus 109 t, but it's not really very helpful. And then what it wants us to do is get an expression for the acceleration of the object at time t. The acceleration at time t is going to be the resultant force. So 9.81 times 10 to the 4 is the upward force. So we need to subtract the weight force, which will be 10 to the 4 minus 109 t. So that's the mass times by g, because remember this is mass, so times by g, so that's subtracting the weight force. Now we've got the resultant force. Now we need to divide that by the current mass, which is this expression here, which we can simplify to 109 t g over 10 to the 4 minus 109 t. That's an equation for acceleration at any moment in time. So in terms of sketching what this looks like on a graph, let's see your acceleration time. What we can see is that as time increases, the weight force acting against the thrust force is going to reduce, so we get a bigger resultant force and a smaller mass. So those two factors are going to add together to give you an exponential increase in acceleration right up until the time that it's empty. And once it's empty, we're going to need to go, it's just going to be a constant acceleration because it's going to fall back down at g. So we're going to get the switch over at this point here, because it's run out of fuel, so the only force acting on it is the weight force at this point. Okay, so that completes this question set.